which recognizes Africa's top scientists and technologists under the age of 42. So that's quite something. That's a lot to live up to. One more thing I wanted to highlight. I think one of Tolu's many strengths is the energy that he puts into being an advisor. So I counted on his CV this morning that he supervised 1 postdoc, 3 PhD students, 11 masters, and 21 undergrads in his time at the University of Rochester. He's really supportive of his people, and when I go to AGU, he's always there encouraging me, really excited to show me his students' posters. And lucky for us, one of his former graduate students, Zhiqi Zhang, will be joining us at RSES soon, working on Herboyer's laureate project. So looking forward to the many connections with ANU continuing. Okay, so with that, I'll hand over to Tolu to tell us about Deep Earth Reassembled.
Thank you very, very much for that introduction. I appreciate all the highlights. It's exciting to be in Australia. I've tried very hard to get to Australia. I mean Australia National University, ANU, and I'm excited to be here. I'm also going to add, as part of the ANU connections, is that I've written a paper with Zach, and we hopefully get it published soon. And so I'm open to collaborations and interesting connections with everyone here. Okay, cool. So it's an honor, as I've said, to be here. So today I want to just share a progress report on the work my group has been doing in mapping the hidden architecture of the deep continents using modern seismic algorithms, but also recently with artificial intelligence, deep neural networks. And I've titled the talk, Deep Earth Reassembled. Those 3 words give you the theme that I'll be trying to put together today. The deep Earth, not going any deeper than the deepest continental lithosphere. I'm sorry for those who think this is going to be a talk about the core. We're literally piecing together the continent's deep structure vertically through its layers and then laterally across the vast terrains. And so I've organized this talk in 3 main parts. From the surface, looking at a new model of the African crust. Then beneath the crust, the upper mantle, exploring layers below the crust using a noise removal method to image layers inside the mantle. And then finally, for those who are still around for the very last part of the talk, I'll explore 2 neural network models that my group has developed to make this type of imaging scale globally over lots of data. So the AI models we'll be looking at will be AkiNet and iRADNET. So the crust, the mantle, and algorithms. That is how deep we are going to go. Okay, good. So when we look at a geological map like that, we see a patchwork of rock ages. You can see on this map in the middle, regions that are ancient, young terrains in between, and rifted margins. So Africa, I'm going to be using Africa as an example for building a new model. And there in Africa, you can see a perfect example of that variety, that geological variety, patchwork of different rock ages. To understand what lies beneath the surface features that we observe, we often rely on geophysical maps. Geophysical maps that inform maps like you see on the right there, heat flow map on the top, and composition maps below. All that sometimes have ingested into them geophysical models, seismological models. And the key point I just want to point out here is that every one of those maps on the right often depend on the accuracy of the geophysical models, accuracy of sometimes the seismological models. If our models of the crust and mantle are wrong, then the geological story we tell globally will be incomplete. So, using again Africa as an example to motivate building better seismological models of the crust. And historically, we've been using active source techniques. More recently, passive source techniques from ambient noise. And in this first half of the talk, then I'll focus in on how we build a new model of the African crust by applying machine learning on developing ambient noise maps. So that's the first part. If you're not used to doing seismology, or if you've not heard about ambient noise seismology, this is the central idea. The goal is to build the image of the crust using waves that are hidden within everyday background noise. Specifically, these are surface waves generated by, amongst other things, ocean pressure that couples into the solid earth. And by taking background recordings of these background vibrations from a pair of seismic stations, like you see on the image on the left, cross-correlating the seismic recordings from that pair, stacking them over long periods of time, you begin to extract ambient noise surface waves propagating across that pair of stations. Effectively, you have illuminated the crust with ambient noise surface waves. And that's what we did. We did that on an immense scale across Africa. The existing seismic models did not have this data ingested into them. And so we created what we called ADAMA, a dataset and model assessment product of the entire African lithosphere. On the left, you're looking at a time station history of 1 million daily seismograms collected from every station that we could find and lay our hands on, recording operating on or near the African continent, where we could find crisscrossing rays between pairs of stations, as you see in the map on the right. So, well, we argue this map is the best coverage of seismic ambient noise seismic data, covering key tectonic features, spanning a variety of craters. I know there are some parts of Africa that are not well covered, but this represented the best data at the time. And so what you do then, like I said, is you cross-correlate this pair of stations. So by cross-correlating every possible pair of stations, you can trace surface waves that are crisscrossing the entire continent. So the panels on the left and on the right are surface waves, Rayleigh on the left, and Love surface waves, bouncing between pair of stations all across the African continent in the slide I showed before, from the closest pairs, so stations close on the top, all the way down to 8,000 kilometers, stations placed 8,000 kilometers apart. I point out that the Love waves often are not measured, difficult to isolate. We're able to extract them and extract the relevant parameters. We're using them to build new maps. So this, we argue, gives us our first true continent-wide glimpse of the entire African continent whole. So that's the data. You extract phase velocities from them. This is just how fast particular waves at particular periods travel. With those pairwise measurements, you can use probabilistic approaches to build seismic velocity models. Malcolm Sandbridge is one of the inventors of this transdimensional approach, as you see there on the right. The algorithm scans the crust, trying every type of combination of velocities with every type of combination of parameterization. And then, constrained by data, you eventually build a map like you see on the left. That is Love waves, waves that bounce side to side at 35 seconds for the entire African continent. Because you're doing this probabilistically, as shown on the right, you can get an error map like that in the lower panel on the right. So confidence tells you confidence. The lighter colors tell you that your maps are more statistically significant, robust. The darker colors suggest higher errors, and that gives you information on how to quantify fidelity in your final model. Okay, so now we've got these maps. We ingest them to build new 3D velocity models. And what we then ask ourselves is there information in this new model from adding this new data, ambient noise data? To answer that question, we take our 3D model on the left and we flatten it into a 2D image like you see on the right. So in the new image on the right, every vertical slice is a depth profile taken from a unique spot on the map on the left. So 1 point, 1 profile, 1 vertical section of that 2D image. So the 2D image is a flattened image of the 3-dimensional velocity model. So when you look at that flattened map, the question you ask yourself is there information there? But when I look at that, that just looks like random static, a random jumble, no obvious pattern. So to make sense of this, we can feed that 2D image, 2D disordered image, into machine learning algorithm so that it can uncover hidden structure, recover patterns that might be hidden in the crustal structure of the entire African continent. And to best convey how the algorithm works, it's called the sequencer algorithm. It just essentially tries to find patterns. I will use the image here. Okay, you've cued me in next Einstein. So put an image of Einstein on the left. You think of that image as horizontal slices. And so maybe that image conveys some important information that you don't want the CIA to find. You disorder it in the middle. You just jumble those horizontal stripes. And now you have information that has been jumbled. It looks like noise, but then if you pass it through the sequencer algorithm, it will take those horizontal strips and try to place those 2 horizontal strips close together to maximize similarity. And it does that in some fancy way, but just that's the essential fundamental idea. So it does that, you take that, put it to the center, and you recover that original image, the jumble that came in when you took the original image and you jumbled it together. So you can discover hidden structure in that middle image if it is there, considering it was built from some fundamental ordered structure. So that's what we did. So remember, on the bottom there is the disordered sizing model of the entire African continent. We have passed that jumbled 2D image through the sequencer. And on the top of that is the result of sequencing the image in the bottom. We then applied a standard clustering technique to now that organized image on the top. It splits Africa into essentially 2 main crustal types, primitive on top, blue with that blue line, and modify on the bottom. And the actual pixel locations of every profile that belongs to that C1 to C4, those different clustering groups, are shown on the map. So essentially, we answer our question, there is information in that new model. That information tells us that the cross probably derived from some primitive type. Modification happens strongest in the wave speeds near the surface and deep down. And these 2 types and the varieties in the second type, when you place them on the map, seem to have some patterns that follow tectonics and geology. And I'll put this final image up. On the right is that taxonomy that derived crustal map. A lot of people have. Yeah. Questions?
Yeah, excuse me to interrupt, but
yeah, no.
how do you define the boundaries between C1, C2, and C4 for previous slides?
So the algorithm essentially takes each pixel as a location and tries to put them in a group. So the boundary is how wide mathematically each cluster group is. So there'll be some pixels that will belong to C1 or might be super close to the boundary of C1 and C2, for example, but there are no hard boundaries. It just comes from defining a priori that there are 4 clusters. And there could be a world where you can say maybe 5 clusters, but there'll be a derivative, say the 5th one might look like C1 or C2. We did a bunch of tests to suggest that 4 is a good number, but you're right. What does the boundary of C1 to C2 mean? That's just pure, in some sense, mathematics. It comes from mathematical definition of those clusters, but good question. Okay, what I want to emphasize is if you look on the left is a known tectonic and geological regionalization of the entire African continent that is independent of what I'm showing you on the right. What we have on the right is purely derived from that pattern recognition on our new ambient noise maps. But the alignment between the two is striking. The level of correlation you see on the map on the right absolutely does not exist in any existing crustal model. So I would argue, if you're going to look at the crust in Africa, stop using anything but a dam. So this proves that our model captures fundamentally new information about how Africa's crust has evolved. We have made that data set entirely open source. Community can use to explore Africa's diverse mountains, basins, rifts. And the hope is we can do this on a global scale. Okay. And on that note, I pause. I thought I brought my water. I can't find it. That's why I'm looking around like a lost puppy. Oh, it's right there. I find it. Any questions before I move to the second part of my talk? So, having defined the crust, let's now shift our focus slightly deeper from the shallow surface down into the mantle. And the key will be to explore a certain question about why the deep roots of continents are layered the way they are. Okay, that might not seem like a puzzling question to you, like, yeah, sure, it's layered. So to ground the discussion, let's revisit a classic idea in structural geology or structural geophysics or geophysical stratigraphy. Well, the idea is the isopycnic hypothesis. Deep roots of ancient continents are made up of a rock that is both chemically light and physically cold. That's the idea. Low density of rock perfectly balances the fact that it is, the composition, the low density coming from composition perfectly balances the fact that it is cold and dense. Otherwise, it will sink and we'll have, everybody will be below oceans and we'll have continents we know and love that we live on and that have existed for billions of years. So the massive roots must float stably over the deeper churning mantle for long amounts of time, creating kind of like an armor plating that protects the continents, giving them their incredible stability over billions of years. And so this idea has been supported by models and data for a long time. So you see on the left, temperature and pressure from deep mantle rocks that have been blasted up to the surface, showing us, if you follow those, the temperature pressure, see the geotherm. That geotherm defines a boundary layer, thermochemical boundary layer, that shows that the continental roots will reach all the way down to 200 to 250 kilometers. Similarly, on the right, you see global seismic maps from tomography, on the bottom in particular, showing thick lithospheric roots, deep continental roots, thick, cold, stable, completely solid throughout, except maybe around 2 decades ago, you start doing seismic measurements as it's been done on the left there. You got a wave coming in, converting at a sharp boundary inside the Earth. And then surprisingly, you start to see distinct horizontal boundaries right in the middle of a supposedly solid, stable continental route, about 100 kilometers, as you see the bottom left there. That's what we're calling the MLD, a discontinuity in the middle of the lithosphere. It is found all over the world. Found in Africa, Australia, and some of you have even written papers about it. Right? So to explain a boundary like this, we have to imagine some complex process, like partial melting, chemical alteration, which seems to imply weakness. And so that paradox, this weakness in a solid, stable, long-living continental root requires rethinking of how you get layering like that. So to solve this, I would argue we need sharper images of that discontinuity. at a variety of locations, and this is difficult to obtain using standard techniques. And so I'll show you why that's difficult and how my group has fixed that problem. Okay. Now we're getting into the technicalities. This is what we call a receiver function. Essentially, that trace you're seeing on the left is a time series showing you where converters are inside the crust or mantle. So that little trace on the left is one profile showing you conversions. And on the right, we have a combination of many of those traces from different locations, in this case, across the US. The problem is, for this type of imaging, is that those converters are buried inside echoes. So converters that you want to get from the mantle are buried within echoes that reverberate in the crust. So the challenge is to remove those echoes, attenuate those loud echoes, so that you can identify the signals coming from deep mantle. You need to use P to S receiver functions as opposed to S to P receiver functions, as opposed to other methods, because you want to build high resolution images of the layer. And so we did that. We removed the echoes using a technique called crisp RF, clean receiver function imaging with sparse radon filters. While our application of this problem to receiver function is new, the idea built from foundational mathematics that has been around since the time of those two handsome European gentlemen, Joseph Radon and Joseph Fourier. I'm not going to go into the mathematical details. I'll give you some intuition about how that worked. But if you want to talk to me about the mathematics, the details, I will very, very happily discuss it. Essentially, we use a radon transform to filter echoes from receiver function. So how does this work? The core of crisp RF is the radon transform. It works somewhat like a medical CT scan, but you're not scanning an object, you're scanning, in this case, or you're not scanning a real object, you're scanning, in this case, a receiver function image. You take that data on the left, you spin it through multiple rotations, giving you projections, different projections into that radon space. The brilliant part is that this projection separates neatly direct arrivals from multiple arrivals, just because you're looking at the data in a different orientation. So that idea of projection, preferential projection that follows the propagation direction, allows you to project those two wavefields into different parts of the radon space and cleanly, surgically remove what you want and what you do not want. So this is what that projection looks like. On the right is the data, receiver function data on the left, transformed into the radon space. The deep mantle targets, so conversions from the deep mantle, project cleanly into that top half. The noisy reverberations of surface echoes project entirely into the bottom half. And in that space, if you can either filter and then do an inverse projection back into the data. What that does, it will remove all those reverberations in red, separate them from the direct phases in blue. So that's just a toy example of the problem. This is a real data example. This is a particular receiver function image from an honest to goodness real receiver function from some location in North America. On the top is a receiver function before crisp RF. In the middle is that same data on the top projected into the radon space. And all we care about are those two arrivals on the top, arriving right around, say, 9 seconds and say 17 seconds. So in the radon space, they're cleanly separated from everything we don't care about. You run the preferential filter across that diagonal, pass through only things in that little diagonal band, do an inverse transform back into the data domain, and you get a clean receiver function image that only shows direct conversions that you care about. So remember that ugly receiver function. This is the clean version. We have removed the echoes from it, and also noise, incoherent noise. We have preserved high frequency sharpness of those distinct conversions. And we can ask the question, what does this new clarity reveal to us? First of all, It confirms that the paradox is real. Those boundaries are indeed there within stable continents. And because our images are now finally crisp, we can begin to figure out what the layering means. So that's what we've done here, and that's the paper Zach are on, hopefully survives PNAS review. So we took the tool, we applied it globally, and we have a map now that shows a massive network of seismic stations covering all continents, stable cratons to other terrains. And what the scale of analysis reveals to us is that there is a universal layering, and these are not just local anomalies. And we can then begin to ask questions like, okay, what and why do we have discontinuities at different portions on this map? By the way, the color map there is just a tomographic model. And the colors inside that image is different groupings for this discontinuity, C1 to C4. And I'll show you how we get these distinct groupings of continental layer. So what we do to get that classification is we take the depth at which we find a boundary. We cross-reference it with other petrological and geophysical models and data, mapping that depth to attenuation, temperature, shear wave velocity, among other constraints. We then feed that into a clustering algorithm, a variety of clustering algorithms. And all of this variety, different clustering algorithms, reveal that there are 4 distinct groupings. You see those groupings on the left. So to answer your question, in this case, you're actually seeing each grouping. Some points in that group are distinct, far away from the boundary of each group. So what I mean here is this point here up there do not lie on the boundary of any grouping. But you might argue maybe some of these points are really one group or another. You might argue that there's some fuzziness to some portion of that data. Regardless, you've got 4 groupings. And if you look, so this on the left is just a 2D projection of that different physical parameters. If you look in the details of each particular type of physical variable, depth, attenuation, temperature, velocity, you see how each group is distinct from another group. So for example, cluster 1 and cluster 2 are distinct in particular in how their temperatures are separated. So I'm looking at the subplot D in the middle panel. Very, very distinct. The temperatures for each of these clusters are distinct. And there are many, many other things that make cluster 1 different from cluster 3. But I'm just pointing out that particular distinction for that class. Okay, so now we've got 4 distinct categories. This extra analysis here on the right that shows that each of these groupings are robust to whatever model you use to create that grouping. And what we argue is that this classification of continental layering suggests that lithosphere is not a single monolithic feature. Here, then, we have taken that grouping, C1 to C4, and we have projected it onto a tectonic regionalization map. So we ask a question, does one group prefer one particular tectonic location in the tectonic regionalization to another? So that's what you're seeing in the bottom there. So to summarize, inside, say, for example, active or near and around active tectonic zones, the layering could be caused by physical melting or chemical changes from violent past. That's what you see there in C1. And then all the way to, say, for example, C2, where in ancient, the layering is located in ancient stable cratons. The temperatures are too cold for melting. There potentially is some mechanism that causes reductions in velocity. It's a localized softening potentially on the microscopic grain level. They slow down seismic waves at seismic wave speeds, but overall, the rock still retains its strength, strong enough to survive for billions of years. So the deep continent, looking holistically, is not a uniform block. It's a complex mosaic reflecting its history. I'll stop there. Pause to take some questions before I move to the last section. I'm running out of time. How much time do I have? Good. Any questions?
We'll do questions at the end.
Good. We'll do questions at the end. So the crust, the mantle, reassembling complex histories across space and in depth. Right, across space gives you some sense of how those blocks in different locations in space have been put together in time, and you can recover it using seismic. Okay, good. So in the last part of the talk, I will show you how you can take some of these algorithms that I've talked about, right? So ambient noise, dispersion measurements, reserve function, denoising. You can take some of these algorithms and you can cast them into AI algorithms. The key will be that we're not going to use neural networks as a black box. We're trying to bake in as much physics into the architecture or the loss function of the neural network. So that's the fundamental idea. So I like to build algorithms. I like to do seismic signal processing, but I'm not going to use AI algorithms without trying to bake in some physics. Okay, so to understand this approach, I think this image on this slide is a good image. It's called the knowledge data matrix, let's say. Most AI models today, I would argue, are sitting in the top left of that knowledge data matrix. They require massive amounts of data. Most of them use zero physics. And if you're to ask, how did he get the answer he got? We don't know. It works well. Essentially, it's a complete black box. Well, some people like that. Most scientists do not. Okay, so I am arguing that for geoscience, we need to move from our top left down into the bottom right. Oftentimes, you have limited training data, but we have massive amounts, relatively speaking, of physical knowledge about how the signals are generated and how to extract information from. So if you can merge the best of both worlds, take the laws of physics or the mathematics of the problem, bake it into our neural network architecture, we can open that black box. We can gain some transparency and better understand what our deep neural network models, our artificial intelligence models are learning. And so just to give you an example of that, I'm showing you this neural network architecture. It's called iRADNET. I've essentially taken that crisp RF algorithm and have transformed it into a neural network architecture. So this is the neural network equivalent of the crisp RF algorithm. You take a conventional physics seismic equation or migration equation on the top, written out algorithmically on the right, and each of the layers in the algorithm is just an unrolling of the iterations in the algorithm on the right. So the left, that data flow is an unrolling of the algorithms of the algorithm on the right. So see that H, that is the kernel of the algorithm. And so you just unroll it however many times you want, K iterations. But each one of that H is a transformation from radon space to data space that mirrors the equation on the top. So what we're using the AI to do is to learn in the absolute most efficient way, absolute most efficient way to solve the migration problem, such that the parameters W, S, and G, if you can squint to find it on the bottom left, are the knobs that you need to tweak to get the migration to work. And because you're dealing with the neural network, you show it many, many examples, but many, many examples that you simulate, and you can then use that algorithm, that neural network, to solve the migration problem. Okay, so that's iRADNET. AkiNet is another neural network architecture. The network gets its name from Kiti Aki, who formulated the elegant physics for extracting surface waves from background stochastic vibration. And what he did was he showed that the correlation between the two seismic stations that I've been talking about follows a specific mathematical shape, and that's what you see in the top left there. If you look at the correlations of the frequency domain, the left of that equation, it is equal to a shape, J0, a Bessel function. Inside that Bessel function, C is how fast a particular wave at a particular period propagates between a pair of stations, assuming that the source covers full circle around the pair of receivers. The crucial takeaway, and that's a simplified derivation of the physics. Its key takeaway, though, is that there is some information in that correlation that follows that physics that can embed potentially in a neural network that helps you say regularize the neural network or make the neural network less opaque. So if you can embed some of that physics into your AI model, you can do a better job of using it to extract surface waves from noise. So because the network honors these exact physics, we do not have to feed it complicated images and claim it's a computer vision problem. We can do this process, raw data, correlation, the frequency domain, and in the top right is what the shape of that image coherence in the frequency domain should look like. It should look like it's a Bessel function. If you can embed that, you can do a better job of solving that problem. That's what we've done with AkiNet. So you're looking at AkiNet as an implicit neural representation for solving the problem. Inside, coming in on the left is a bunch of frequency points, and coming out of the neural network is speed of wave as a function of period, the dispersion they're trying to extract. It's a zero-shot solver. You don't have to train it, because in the loss function in the bottom is the form of the solution. So you condition the loss function to minimize the difference between the prediction and Aki's SPAC formulation. So it literally learns the shape of the solution. So the neural network is a representation of that solution. We can get many, many dispersions. You can then do the downstream imaging problem I showed in the first half of the talk. Okay, so this is in practice what it looks like. 40 layers, 40 neurons per layer, about 70,000 parameters for one zero-shot solution, for one dispersion extracted from coherence. If you had to compare this model with another AI model that does a similar problem, DisperNet, that's 12 million parameters for DisperNet, solving the problem like computer vision. This is 70,000, 2 orders of magnitude smaller. I know what exactly is in the model, and I know how I've conditioned it. So I know its failure modes and things like that. And then we also do a bunch of other things, some regularization at the back end and things like that to stabilize it. But again, simple, lightweight, and transparent. Okay, how does it perform? AkiEstimate is another type of model built by Hawkins and Sembridge in 2019. Does the same thing, but using kind of a nonlinear iterative inversion process. And you're seeing AkiEstimate doing its thing. Again, in the middle there is the data in blue. And the goal is to try to mimic the data in blue by tracing out that red curve. To trace out that red curve, you have to correctly solve for that C. So we're trying to get C from the blue. So we're trying to get this red curve from that blue data. And we know it's good when our prediction matches observation. So this is another way to solve the problem. And this AkiNet doing the same thing compared to AkiEstimate. So we're putting AkiNet through a stress test. On the left, clean Rayleigh wave data. AkiNet performs just as well as AkiEstimate. Again, the data on the top, the solution C on the bottom, AkiNet in blue, AkiNet in brown, AkiEstimate in blue. On the left, good Rayleigh wave data. But then if you look at on the right, slightly poor data, highly noisy love wave data. Again, you can see that because the blue is not that large. It's got a lot more jitter to it. AkiEstimate fails. AkiNet does a better job of tracing the solution. And so in this case, in this particular case, where the data is a little more noisy, more complex, more complicated, AkiNet is doing a better job. So getting accurate log wave and Rayleigh wave data, C, those bottom curves, together are important if you want to build models that are anisotropy aware, that have some insight on directional dependence to seismic wave speeds. So that can, say, for example, help you tell how the rock fabric is oriented and revealing things like deformation history. Okay, so that's AkiNet. Okay, so we've got AkiNet, we got iRADNET. What are we going to do going forward with this? And we want to do a better stress test, even better stress test of AkiNet and other techniques. So what we're doing is we are building a corpus of training data so that we can benchmark AkiNet and other existing models, improve AkiNet, say, for example, but also show why and in what cases AkiNet performs well. So what you're looking at on the top left there is the geometry or configuration for a synthetic experiment, the pair of stations and noise sources surrounding it. We vary the velocity model, sample a large suite of different types of velocity models. And then in the bottom two panels, you see the cross-correlation function, the one in white in the time domain, the bottom in the frequency domain. Because we are synthesizing this, we actually know the solutions, and the solutions are overlaid. But in general, on the top there is how people will try to extract group velocity from the signals in the bottom. So you have these F-tan images. The goal is to take those F-tan images and to draw out that green curve. And so in typically other neural network models, you show them a pair of those images on the top, and they learn how to trace out that curve. And so we want to build these corpus so we can then begin to benchmark AI models that do this task, AI models that solve dispersion. Okay, let me stop there and do a recap, right? And then take some questions. So what have I shown you, right? I've shown you that the deep continental lithosphere is not uniform. It's not uniform in the crust of Africa. It is not uniform across the globe in the mantle. It is definitely shaped immensely by its tectonic history. In the young continents, as just an example, layering is driven by melting, while inside the oldest ancient cratons, potentially shaped by weakening at the microscopic level that allows us to preserve strength at the long time scales. I've also shown you that to map these structures out globally, we have to use classic seismic algorithms, but that we can also scale the seismic algorithms using AI models. And the key is to do that in a principled, physics-informed way. What will that give us? That will give us powerful, transparent alternatives to black box machine learning models that can scale globally, so we can begin to build global models that help us answer interesting questions. Okay, oftentimes people start with the credits. I will end with the credits. So I'd like to thank my incredible lab. This is what it looks like right around circa 2026, and collaborators who've made some of the work possible. And I also say, yeah, I'm beginning to look to grow the group. So if you're interested or you know someone who is, they can come find me. Now you know a flavor of some of the problems we work on. I will leave a picture of around 2024, what the group looked like. Some of these members are coming to an office near you. And this is a broader flavor of some of the work we have done in the past and we look to continue to do in the future. So earthquakes, imaging, marine geophysics, signal processing, high performance computing, and volcanic hazards with hydroacoustic sensors. On that note, I will stop and take questions. Thank you.
Thank you very much, Tolu. We've got plenty of time for questions. Who would like to? Thank you.
Thank you. Very exciting talk. Very thought-provoking. So actually, I'll start actually with the question in the first part, which is the crustal image. I mean, you used the statistical approach to do the inversion, which gave you both the velocity model and the uncertainty. But then later, you sort of, say cut the uncertainty part, but just like look at the velocity model and then give us some, looking at the sequence of that. I'm just like curious. Where is that uncertainty?
How do you use the uncertainty?
Right.
Yes. If good question, right? So the question would be, how do I, so anytime I have to ask a question of confidence and trust or potential improvements, I use the uncertainty. For example, if I was to use the velocities for a downstream inference on, say, inverting for temperature, inverting for composition, inverting for pressure, I will bound my numerical estimates with the confidence estimates I have. So when I'm doing concrete numerical inference with the velocity models, and we do that often, right, in a variety of ways. So that's one way to do it. Another way I could do it is to say, I could take that, any map I have, and overlay on top of that map the uncertainty map. So even my my sequenced image, my classification, my taxonomy of Africa, I can overlay on that the uncertainty map. So what I mean by that is, it is obvious to me and to anybody who uses the model correctly with uncertainties that anything that you say about West Africa should be taken with a grain of salt, right? Because I know that there's high uncertainty in West Africa. So that's one way to do that. But I can bound that with a numerical error and not say throw everything out. So you can use it with this caveat. But also, that's an opportunity for improvement in the model. So if I want to improve any model of Africa, I should go get more data in that particular region. I probably will not improve the resolution of the model, say, in and around East Africa at the scale of, say, station spacing. So that's a done deal for this model. However, if I want to do higher resolution imaging, higher spatial resolution imaging, you could. So that's how I would use the model. You provide all the inference, but you also provide the confidence estimates. And that's potentially my answer. I don't know if that answers the question. If anybody wants to say a little bit about that. So for example, I'll just show this map. So this map, the map there on the left is just me color coding uncertainty. So green is good to go. Blue is take it easy. Dark red is super bad. Red is don't go there. So meaning how confident I am of every pixel. And then I've made that pixel maybe at 0.25 degree spacings each dot there. That's not the true resolution of the model. That's just me saying, okay, that's how I want to look at the model. Make sense?
So the structural maps that you've shown across the manifold, you've showed us 2D maps, right? But then, so we agree that those structures are 3D. So with the algorithm, are you able to basically make clusters based on depths, or just based on a depth integrated profile?
So these models are not real true 3D models, right? They're just quasi 3D models. So they're just essentially 1D models stacked together. There are probably complexities in the Earth, in Africa, and across beyond Africa that have real true 3D structure, meaning interfaces that dip and dive and things like that. I've talked to Ping, who saw that in New Zealand, for example, across faults. So you can build models. Malcolm's an expert at this, where you try to have the data tell you which 3D parameterization is good. So for example, instead of looking at everything as a 1D pixel, you can think of them as, I don't know, blocks that have sharp, like planar features, something like that, and many, many varieties of that. So this is a bias that we are placing into building models. So that's when you think about it. Does that answer the question from just the way I built it?
Yeah. So you think you can
go one step?
That's 3D step, or Or is that something that?
No, we can either look at this as some kind of alias 3D view and see how things vary from pixel to pixel, say for example, at depth. So I can show you, say, for example, a map of the topography of the moho, how the moho like bends, and you'll get a view of that. But that's an alias view, right? That's a view where I have kind of sliced through the 3D structure at 1D, whatever the resolution spacing. I can do that. I can do more than that if I had the computational power and the interest to do that as well. I can just say, okay, let's be very, very flexible, not have 1D models, have true 3D models. You can do that as well. But we haven't done that here, just to be kind of transparent about that.
Can I give him a question?
Yeah.
So maybe following on from this slide here, and comparing the two different algorithms you're talking about, so you focus just on the LAD using the CRISP-RF?
Yes,
Have you done
indeed.
anything for the MOHO using the CRISP-RF? And I guess in
question.
particular, looking
Good question.
at can you compare this model for the
Exactly.
aptitude
Gotcha.
using the MOHO?
Gotcha.
Because this is based on the velocity models.
Yes, exactly. Yes. Yes, indeed. Simple answer is we have not yet.
Yeah.
But we will do that next. And what we're hoping to do next is actually just scan the moho across the entire East African rift.
Yeah.
Because with residual function, you really do need boots on the ground. I can't do this. The stations can be anywhere spanning the volume. It has to be literally directly above. So you're out of luck there. So you have to actually have station density to map through moho geometry. And that's what we're going to do. And you can then imagine for it to do this globally, right? And you and many other people have done it in very high resolution in different portions of the world. But that's what you'd want to do. You'd want to create both a velocity field and topography field of the moho that you have to do some kind of joint inversion that gives a model. But then the topography will only, you have some uncertainty too on that topography. Yeah, but we haven't done that yet.
Morocco stuff is what caught my eye.
Gotcha, right? For those who do not know, that's right around there. Did you wait? Exactly. There we go. Thank you, Megan.
Very different between
there we go.
their one piece.
Gotcha. Interesting. Yeah. No, very good questions. Yeah. And a lot of people care about the topography of the moho for good reason. And we could do that right about very quickly. What I'm trying to do is like take things very systematically and say, okay, I'm going to give you the best of my ability model I can offer. And so what we're going to do in the case of moho topography is to clean it up, both with in PS and S to P, so that you can do joint PS imaging if you want, but you can also do joint PSSP imaging with surface wave whenever you're ready. But then that would be clear. Clean data that I can ingest as well as something like a product type way of doing things. I give you one product, every one product. I can swear by it that nobody will give you the better than that. And then you can do with it whatever you want. Yeah. Yeah, Malcolm. Oh, sorry.
It's not good at all.
Hey, Tom. Yeah. Did I pronounce his name correct?
I think how AI definition. For categories,
Gotcha.
how are you getting like compulsion from that?
Gotcha. That's a good question. Very good question. I would love you to answer that question. But so how do I say that C1 is melt or C2? Okay. Yeah. Let me see if I can answer that very, very. Okay. So here, if you just look here, right? Let's just say C1, C2, right? So this is C1 and this is C2. And then we ask, so we essentially take a grid of the different mechanisms and we ask what physical parameter must you have to get rocks to melt at a certain composition. And we scan C1, C2, C3, C4 and realize only C1 can do that, right? And then we also note after the fact that it turns out the stations in C1, the stations here, I guess it's C1, it's blue, right? We then map them to space, right? Now we map them to space after we know that the temperatures here are above or close to melting, that they preferentially sit on rifts and Phanerozoic terrain. So that's how we map it. We map it after the fact. We do all this clustering to get the physical variables, and then we ask which mechanism can create layering at that depth with those physical variables, and that match the tectonic feature after the fact. Yes. Yeah, they include temperature, shear wave velocity relative to some mean, attenuation, and other, yeah. So you'll notice high attenuation, high temperature, low shear wave velocities all seem to indicate conditions that are favorable for partial melting. That's the reasoning we go through. Does that make sense? Yeah. And we do the same reasoning for metasomatism, and I can walk you through that reasoning, but that's what we do. Make sense? Yeah. Any other question?
Last question for Malcolm.
I had two, but
drop two. I'll answer one and we'll continue conversation on the second one. Okay.
So in the radon transform, the direct and multiple, the space you transform into, as I understood, was curvature.
Yes.
So my question is, why is it that multiples have a different curvature from direct arrivals? So why do they separate?
Why do they separate? Yeah, that's a good question. Simply, if you look at it, it is the second, it's the move out. So the direct waves are just coming in with a certain move out, meaning the more vertical rays and which one's more vertical arrive slightly later than the ones that are a little bent when they're coming in for the direct waves. So they just have that positive move out. For the
relative move out.
It's a relative move out. Yes, exactly. That's the idea. Now, when we write out in a simple 1D Earth, you write out the true move out equations and you try to approximate it by some like Taylor expansion. That's prefactor to that second derivative becomes positive for the direct waves and negative for the multiple arrivals. That's just it. So that's why they have that curvature. Obviously, that's a simplification of through Earth structure. You can imagine other move outs and you can write those equations out. And people have done it. People like Bostock and co-authors have done it for, say, complex anisotropic media. And they won't call it radon projections, but maybe one of the authors radon projections, but that's what it is essentially. You can go from projection to wavefield to projection in the equations themselves, in the wave propagation equation itself. Yeah, I'm just using it as a seismic signal processing tool. Answer the question? Good. Second question. I like the philosophical question. Let's do this philosophical question.
So I wanted to take you back to your AI and automating a process which humans do.
Yes.
To combat the stack. Computation and expert seismology. What is the value argument of replacing it with AI? Is it a speed issue? Is it an accuracy issue? No doubt it's an attract students to project issue. But here's my more provocative part. If everyone did this, are we just moving towards training a generation of seismologists that don't recognize seismic rooms?
It's a good question. Spectacular questions.
You're not the first person who's asked.
Let me answer the question the way I see it. No. Okay. What's the value argument? So first of all, I did not want to do AI because I could not understand it. So I think the value argument is there something about taking the problem as we know it? Obviously, you have to understand it to be able to translate it. So I don't think we are losing anything that way. Right now, I'm kind of arguing, okay, this is like principled. I know what's going in there. So I'm not losing anything. So, but then we are getting the best of both worlds. A bunch of papers you did back in the days were like, okay, automatic differentiation, blah, blah, blah. They carry over and you can benefit from that. So it's almost like you're building a seismic algorithm with a new, say, engineering frame. But the science, I don't think you lose the science if you follow this explainable AI framework. So that's one value. Second value argument, I'll just be candid with you, is classic algorithms need a lot of tuning. And so I'm going to hire a student that's going to spend a year tuning algorithms. Let's see if some of that tuning can be taken over by the principled AI frameworks. That's the truth. I want to go global, but I can't go global by looking at every single wiggle. Wiggles are beautiful. I love wiggles. I want to go global, right? So I want to scale. I want to scale. So in principle, how I'm going to scale AI is not too bad. And then from recruiting students, well, that's really the other reason I'm doing it, right? Because there's money in it. DOD, Donald Trump wants it. I'll stop there.
All right. Thank you, Tolu. Good place to end. I'll just say we've got afternoon tea outside. There's some food. You can grab a cup, get some tea. So please hang around for a little while. Chance to talk to Tolu some more. And then this evening, we're also going to Dear Prudence, connected to Verity Lane for dinner. And there's going to be a few more people there on their way, visiting on their way to SETI as well. So there'll be a large group. So if you want to come along, feel free. All right, let's thank Tolu once again.